Hi, physics. Mr. Janowski here. This is the Chapter 13 study guide, and this is problem 2. So we have a spaceship that lands on the moon, which has that radius and that mass, which is to say the moon has that radius and that mass. And we need to figure out what is the value of g if you're on the surface of the moon, and then what would be the value of g if you're at that height above the moon. So we'll start with, where's the cursor? There we go. We'll start with step, So for part A, we want to know little g on the surface. So this will be question mark. And what are the units of this? We've been using little g basically all year long. So its units will be meters per second squared. And part B, what is little g when we're at this height? So little g, height, altitude, whichever you want to call it. Also meters per second squared. All right, so part A is really easy. It's just plug and chug. So what we have is little g is equal to, and then check the footer, find the formula you want for little g, and you'll get big G times big M over r squared. So plug in your value for big G, 6.67 times 10 to the minus 11th, and your value for big M. Okay, so is big M the mass of the spaceship, or is it the mass of the moon? It's going to be the mass of the moon. 0.35 times 10 to the 22nd kilograms. All of this divided by r squared. So in this problem, r is just the radius of the planet. I'm sorry, in this part of this problem. So this radius is 1.74 times 10 to the 6 meters, and this quantity gets squared. So if you do all this in the calculator, what are you going to end up with? You're going to end up with 1.62 meters per second squared. Put a box around it, and then do step, well, we solved for the right thing. We gave it the right units. And does this number make sense? Well, little g on Earth is 9.8 meters per second squared. So we've got a smaller number than that, but the moon is smaller than the Earth. It has less mass, so its surface gravity is going to be less strong. So yeah, this number makes sense. So maybe the one pitfall, and this is going to be common throughout this test, excuse me, is you've got to avoid the red herrings. So I really need to switch back to red for this. So if we're looking at the problem, what's the red herring here? The red herring is the mass of the spaceship. Can I draw a fish with my Wacom tablet? Yep, close enough. Kind of a funny looking fish, but that's our fish. Yeah, the mass of the spaceship doesn't matter. When you're determining things like little g, the mass of the thing that's sitting on the surface has nothing to do with what little g is. So that information is just there to distract you. And yeah, that kind of thing, the red herrings, it's a big part of this chapter. So now on to part B. So now we need to figure out the value of little g if we are at that height above the surface. So I think a sketch is going to be really helpful here. So we've got the moon, and the moon has some radius. So radius moon, capital R. Radius moon. And that radius is this number here. So in part B, we're at some pretty big height above the surface. So this number is basically twice as big, not twice as big. It's bigger than that number. So yeah, we're going to be at some height here. That looks good. So here's where we are for part B. And yeah, that'll work. Yeah, we're at this height, 2.50 times 10 to the 6 meters above the surface. So the value we need to plug in to the formula is not going to be the radius of the moon, and it's not going to be this number. It's going to be the sum of those two numbers. It's going to be both of those plugged together. So this will be our R for part 2. So hopefully that makes sense. Yeah, if you make the little sketch, it should be clear. I highly recommend making the sketches, because if you're not making the sketches, if you're just grabbing numbers off of the page, it can be really easy to just get really confused and lost. So you make the sketches, and it ends up being not so bad. So anyhow, this R here is, well, first it's the radius of the moon, 1.74 times 10 to the 6 meters, plus the height we are above the surface, 2.50 times 10 to the 6 meters. So if you do all that, what height do you get? You get 4.24 times 10 to the 6 meters. So yeah, we'll need that number. So from here, it's just plug and chug. G is equal to big G M over the R we're going to use squared. So again, 6.67 times 10 to the minus 11th. Mass of the moon is still the same, 7.35 times 10 to the 22nd kilograms. And again, we're ignoring this number up here, so I'm just going to cross it out to make it clear that we don't like that number. It's just there to distract you. Still a red herring. So now we're going to divide this by that number we just figured out squared. 4.24 times 10, sloppy, times 10 to the 6th meters, and just that gets squared. So if you do all that, what do you get? You get 0.273 meters per second squared. So put a box around it, do step, we solved for the right thing, we gave it the right units, and we got a fairly small number. So does that make sense? Yeah, notice this number, our answer for part B, is smaller than our answer for part A. Well, if you're some big distance off of the surface of the moon and you drop something, it makes sense that the gravity, the local gravity, which is another name for little g, is not going to be as strong up at this point up here as it is right on the surface, because you're further away from the mass of the moon. So it does make sense that you get a smaller number. So we're happy with this number, and we give it a check. So again, key takeaway, make the little sketches. The little sketches make these problems much easier to think about. And they also show your physics teacher what your thinking was, and your physics teacher appreciates that. So hopefully you found this helpful.